So, in the last few lectures we have looked at the temperature disturbance due to a point source, point dipole, point quadrupole, related those to the temperature fields in the temperature solutions that you get by a separation of variables procedure. Okay. And then we were looking at what is called a distributed source. Okay. We are looking at the temperature field due to what is called a distributed source. So, in that case you have some particular region, volume V, okay, where you have a distributed volumetric source QV of x per unit volume per unit time. Okay. And the temperature field is given by k del square T plus QV of x is equal to 0. Okay. X is the location at which we are trying to derive the temperature field. This is the differential equation for the temperature field. And I had drawn an analogy between this and a point source. Okay. So, if I just have a point source at some location x s, okay, and the observation point is x, okay, and I want to find out what is the temperature field due to this point source of strength q. Okay. The equation in this case is k del square T plus q delta of x is equal to 0. That is the equation in this case. The solution is T is equal to 1 q by 4 pi k into x minus x s, and the heat flux was equal to q into x minus x s by 4 pi k into x minus x s the whole cubed. Okay, these were the temperature and the heat flux. Now, to calculate this for this distributed source, what I had told you is that we can separate out this into a large number of differential volumes. Okay. Okay. I had used the prime for the volume. Okay. Okay. So, this will be delta V 1, delta V 2, etc. Okay. And any typical volume I will call it as delta V n. Okay. The total amount of heat generated in this differential volume, okay, is going to be equal to, if the centroid is at location x n, okay, total heat generated okay, not heat generated per unit volume, but the total heat generated is equal to, okay, delta V n prime q of x n prime. Okay. Okay, where the source location I have written it with a prime, q of x n prime times delta V n prime. The temperature field is obtained by the equation k del square T plus q n. Okay. Okay. Therefore, the temperature field due to this is going to be equal to delta V n prime q of x n prime by 4 pi k into x minus x n prime, okay, where primes denote the source point, okay, where the primes denote the source point, okay, okay, where the primes denote the source point. Okay. And if I sum this over all of these volumes, okay, if I sum this over all of these volumes, I will just get I is equal to n is equal to 1 to n, okay, over all of these differential volumes. In the limit as delta V n prime becomes small, okay, if you take the limit as the volume goes to 0, this just becomes an integral, okay, dV prime qV, okay, this is a volumetric source, okay, I should note qV of x prime, okay, by 4 pi k into x minus x prime. Okay. So, that is the temperature field due to these source points. Okay. Let us look at a practical example. Okay. Let us look at a practical example. Okay. So, therefore, the temperature field is just an integral over the source points dV prime of the volumetric source per unit volume per unit time divided by 4 pi k into x minus x prime, and the heat flux is equal to integral dV prime of qV of x prime into x minus x prime by modulus of x minus x prime whole cubed. Okay. So, that is for a distributed source. Okay. So, that is the temperature field for a distributed source. Okay. Let us look at a concrete example, okay, and that is heat conduction from a wire. Okay. So, okay. Okay. I have a wire of length 2L, okay, in the region y is equal to plus L to y is equal to minus L. Okay. I have a wire of length 2L in the region y is equal to plus L to y is equal to minus L. Okay. And you have a source, energy source, okay, Q per unit length per unit time, okay, emitted from the wire, and we want to find out what is the, okay, let me write this a little clearly, any source Q per unit length per unit time emitted from the wire, and we want to find out what is the temperature field around, okay, in this coordinate system. So, first things first, this wire is infinitesimal. The source per unit length per unit time is equal to Q. Okay. The source energy per unit length per unit time is equal to Q. Okay. Therefore, the volumetric source, that is the energy per unit volume per unit time per unit volume per unit time, okay, is equal to Q delta of x delta of z, okay, because the source is, if you consider the wire of infinitesimal thickness, then there is a source only when x is equal to 0 and z is equal to 0 and y goes from minus L to plus L. Okay. There is a source only when x is equal to 0 and y is equal to 0 and z is equal to 0 and y goes from minus L to plus L. Okay. Since I have used primes for the source points, I will put primes over here. Okay. So, what is the expression for the temperature field? Okay. T is equal to integral dV, okay, Q of x prime by 4 pi k into x minus x prime. Okay. This volumetric integral has integrals over x, integrals over z. Integral over y is only from minus L to plus L dy, because the wire is present only from minus L to plus L, okay, into q delta of x prime. Okay. These I should wrote are the source points. Okay. This is dv prime, the source location, okay, the integration over the source location. Okay. So, dx prime, dz prime, and then dy prime between minus L and plus L, delta of z prime by x minus x prime. Okay. And I can expand out the denominator as x minus x prime the whole square plus y minus y prime the whole square plus z minus z prime the whole square, whole to the half. Okay. So, that is the expression for the denominator in terms of x prime, y prime and z prime. Okay. Integral minus infinity to infinity. Okay. Note that integral minus infinity to infinity dx prime delta of x prime times any function of x prime is equal to the function at the location x is equal to 0. Okay. Okay. That is the fundamental property of the delta function. Similarly for z. Okay. So, I can remove the integrals and the delta functions and just evaluate the function at x prime is equal to z prime is equal to 0. Okay. I should put a factor of 4 pi here. Okay. So, I can take the q by 4 pi k outside. Okay. I have substituted x prime is equal to z prime is equal to 0, okay, because the wire is stretched along the y axis. Okay. And you can do this integral. I will not go into the details. What you will get is that this is equal to q by 4 pi k log. This is the natural log. Okay. L plus y plus square root of the whole square. Okay. Note that once I integrate over y prime, the result is no longer dependent upon y prime. Okay. So, this x square, I am sorry, this should be z square. Note that x square plus z square root of is basically the distance from the axis. Okay. The square root of x square plus z square is basically the distance from the axis, okay, from the y axis. Okay. Now, if we consider the particular case, so this is the expression for the temperature field, and we would like to know if this is consistent. Okay, we would like to know if this makes sense. Okay, so how do you do that? You look at certain limits. You look at the limit where either the distance from the wire is much smaller than L, or the distance from the wire is much larger than L. Okay. So, let us restrict ourselves, okay, to observation point in xz plane x 0 z. Okay. Let us restrict ourselves to the observation point in the xz plane. Okay. In that case, okay, the temperature field simplifies. T is equal to q by 4 pi k log of L plus square root of r square plus L square by minus L plus square root of r square plus L square, where r square is equal to x square plus z square. Okay. So, that is the solution for the temperature field along the xz plane where y is equal to 0. And we can ask what happens if the distance from the wire is much larger than the length of the wire. Okay. What happens if the distance from the wire r is much larger than the length of the wire L. Okay. In that case, I can divide throughout by r. Okay. So, I will get T is equal to q by 4 pi k into log of, okay, L by r plus square root of 1 plus L square by r square by minus L by r plus square root of 1 plus L square by r square. Okay, dividing numerator and denominator by, okay, 1 over L square plus r square. Okay. And in this case, if you do an expansion in the expansion in L by r much smaller than 1, okay, then root of 1 plus L square by r square will be equal to 1 plus half L square by r square. Okay. So, I will get 1 plus L by r by 1 minus L by r. Okay. So, so this will be equivalent to log of 1 plus L by r by 1 minus L by r, okay, okay, into q by 4 pi k. Okay. Okay. And that is equal to q by 4 pi k. Log of 1 plus x is x plus x square, log of 1 minus x is minus x plus x square. So, I will just get 2 L by r, okay, it is equal to 2 q L by 4 pi k r. Okay. So, that is what I get when the distance from the wire is much larger than L, okay, 2 q L by 4 pi k r. Okay. If the distance from the wire is much larger than L, then the solution that I should get should be the same as a point source. Okay. If the distance from the wire is much larger than L, what I should get as the result is the point source in 2 dimensions, in 3 dimensions. Okay. That source strength is going to be equal to Q, which is an energy per unit length, okay, into the length that is 2L. Okay. So, this is basically the source strength of a point source if the wire length is much smaller than the observation point. The wire appears as a point source of source strength 2 QL, because Q is the energy generated per unit length per unit time, 2L is the length, and therefore 2 QL is the energy generated per unit time from the wire. Okay. So, when you go sufficiently far, the wire looks like a point source of source strength 2 QL. What happens in the other limit? Okay, in the other limit, where r is much smaller than L. Okay. Note that t is equal to q by 4 pi k log of, okay, L plus root of r square plus L square by minus L plus root of r square plus L square. I can write this dividing throughout by L whole square plus 1 and these L's will cancel out. Okay, if I take L out as a common factor, okay. And you can see in the numerator I just have a factor of 2. Okay, I just have a factor of 2 if r by L is small. Numerator I have a factor of 2. Denominator I do not have a factor of 2. 1 plus r by L the whole square root of. Okay. So, this will basically become log of 2 L by, okay, one by 2 into r by L the whole square. I am sorry, this should not be 2 L, this should just be 2. Okay. Which is equal to q L by 4 pi k into 4 L square by r square. Okay, sorry, log of 4 L square by r square. 4 L square by r square is the square of 2 L by r. So, I will just get q So, what the limit we have taken is r is very much smaller than L. Okay. The limit we have taken is r is very much smaller than L. Okay. That is, the distance from the wire is very much smaller than the length of the wire itself. So, the wire in the xz plane, okay, in the xz plane, the wire is perpendicular. The perpendicular wire is, sorry, in the xz plane the wire is perpendicular, it is in the y direction. Okay. In the xz plane the wire is perpendicular, it is in the y direction. If the distance r is much smaller than the length of the wire in the perpendicular direction, it appears like heat conduction in 2 dimensions. Okay. It appears like heat conduction in 2 dimensions in the xz plane. Okay. If the distance from the wire is much smaller than the length of the wire itself, this configuration appears like conduction in 2 dimensions. And for heat conduction in 2 dimensions, the temperature, okay, if you solve, okay, del square T plus Q is equal to 0, Q delta of x is equal to 0 in 2 dimensions. You will find that in 2 dimensions the del square goes as 1 by r d by dr of r partial t by partial r plus q delta of x. This is equal to 0. Solution for this is, okay, this one, okay, in 2 dimensions. Note that this solution in 2 dimensions increases proportional to log of r or minus of log of r, okay, as r goes to infinity. The temperature does not decrease to a constant value in the limit as r goes to infinity. Okay. The reason is because in 2 dimensions we do not have solutions for the temperature field which decrease to a constant or decrease to 0 in the limit as r goes to infinity. Okay. It is only in 3 dimensions that we have the temperature field decreasing to 0 proportional to 1 over r for a point source. Okay. So, therefore, in 2 dimensions we do not have the temperature field decreasing to 0. So, to summarize what I have said about the distributed source so far, okay, the distributed source follows del square T plus QV of x is equal to 0. You can consider this distributed source to be a sum of a large number of point sources. Okay. You can consider the distributed source to be the sum of a large number of point sources. And therefore, you can just assign a delta function, each point source is in a differential volume. You can assign a delta function at the centroid of that volume to each of those point sources, and just by doing a summation and converting that into an integral, you get this is equal to integral dv prime qv of x prime by x minus x prime, and there should be a 1 by 4 pi k, and the heat flux is equal to 1 by 4 pi k integral dv prime qv of x prime into x minus x prime by x minus x prime whole cubed. Okay. Everything that we have done so far is in an infinite medium. Okay. Everything that we have done so far is an infinite domain. Okay. There are no boundaries anywhere. Okay. What do we do when there are boundaries in the domain? Okay. So, obviously, the temperature field has to satisfy the boundary conditions. The temperature fields that we have got so far due to sources in an infinite domain, okay, due to multiple sources in an infinite domain, all decrease to 0 in the limit as r goes to infinity, okay, in this 3-dimensional coordinate system. Okay. What happens if we had some boundary here? That boundary could be either perfectly conducting or perfectly insulating or something in between. So, what will happen if you have a boundary in the domain? Okay. So, that the use of this method of point and distributed sources for domains with boundaries, I will start in the next lecture, okay, and complete this section on solution of diffusion equation. Okay. So, we will discuss what happens when you have boundaries in the domain in the next lecture, and then we will go on to the next topic, which will be forced convection. I will continue the solution of the diffusion equation in the next lecture. I will see you then.